All right, so we just finished up our sort of basic Algebra 2 review. We didn't review everything from Algebra 2, but we reviewed some of the major concepts that allow us to go forward, like factoring and things like that. And so today we're going to start really looking at functions in more depth than we've sort of gotten into in Algebra 2. We're going to look at them more closely. All right, so a lot of terminology today. Today is a big vocabulary day. So functions. You all probably know, we'll just go over it really quickly, but what's the idea of a relation is actually even more fundamental than the idea of a function. And a relation is just any correspondence I'm not going to make that any correspondence between two sets. This is like the worst part, is writing vocabulary on this thing. Between two sets, as you know, right? And so an example of a relation, we can display a relation, and it can be any types of sets, right? It doesn't have to be numbers necessarily. It can be sets of objects or things or whatever. Anytime we take two sets and we relate them to each other, we correspond them to each other, we match up pairs from one set to the other set, that's a relation, right? And we can sort of visually display any type of relation using what we call a map, which you probably remember from Algebra 2, where we take, okay, let's say we'll make in this particular function, all of our elements of our sets will be numbers. So let's say we have 1, 2, 3 on one side, and the other side we have 8, 9, and 10. And so if we take these and we pair them up, like say 1 goes to 9, 2 goes to 8, and maybe 3 goes to 11, right? This is an example of a relation, right? Now, a function is a type of relation, right? And a function is a special type of relation, right? So, does anyone remember what the difference is, or what makes a function special and makes it different from just any other normal or just any other run-of-the-mill sort of relation that's not a function? What? There's probably you're getting at the right idea, but is there a better way to sort of a more precise way to say that?
The domain doesn't have repeating values.
I suppose saying repeating. Is there a different way of saying that? That's more. Repeating sort of gets at it, but not quite.
Same number relates to
more than one of the range.
Yes, yeah. Every single element of one of the sets, right? Which that set we're going to call the domain. And so we sort of have to know what the domain is ahead of time, which is usually just defined ahead of time. This set is the domain. The other set is the range. Right? And we think of the domain as the input and the range as the output. Right? And a function is a special type of relation, right, where the domain, elements of the domain, are paired with no more than one element of the range. So if I asked you, for instance, if we looked at this mapping right here, and I said, okay, well, what element is 1 paired with? If you said just 9, then that's so far so good as far as it being a function. But if you were to tell me, well, 1 is paired with 9, but it's also paired with 8, that wouldn't be a function anymore, right? So in a function, it's a relation where every element of the domain is paired with only one element of the range. Right? So it's a special type of relation here. Right? And once again, we think of the domain as the input, right? We sort of, when we're referring to functions, we sort of phrase it like a question. We say, okay, well, if I'm given one element of the domain, what element of the range does that correspond with? So we put in 2, and we get out 8. We put in 1, it spits out 9. We put 3 into this particular function, it spits out 11. So we think of what's going on in between here, how these things are linked up, this is the function, which I'll call f here. We use, of course, the letter f to denote function. So everything that's going on right here with these linkages is the actual function itself. It takes this set and it links it to this set, right? And so, there's more terminology than that, I guess not. I'll just give you some examples, I guess. All right, so for instance, I don't know what you're doing. I'm going to give you a couple mappings here, and I want you to decide whether these relations, they'll all be relations, whether they're functions or not, based on the mappings. And we know that, and I'm also going to give you some that instead of using mappings, I'm going to use ordered pairs to represent the relations as well. So, for example, for this first one, let's say we have A, B, C, D, and E, right? And over here we have 1, 5, wow, it doesn't look like a 5. 1, 5, 9, 11, and that'll just be it. And I'm going to link these like so. So there's this first one. Here's my domain. Here's my range of that relation. Right, and then I'll do another one down here. Let's do K, J, G, and E. And over here we'll do 12, 3, 2, and negative 6. Right, and let's say that the K corresponds to 12. 2. J goes to negative 6. E goes to 3. And G goes to 3. All right, of these two here, which one is a function and which one is not? Yep. Exactly, the top one is a function. The bottom is not. It is a relation, of course, but it is not a function. Right, so that's basically what we're trying to get at with functions versus relations there. Some other basic terminology that might come up. And on pages 56 and 57 of your text, that's a good place to look if you're looking at a vocab word going, I don't know what that means. Turn to those pages. All the vocab words are pretty much in bolded there, so you can sort of see what's going on. And so some other terminology. So other vocab, I'll just call this. Sort of just learning a new language here. Nothing, no new concepts, just new ways of talking about it, right? The y value that corresponds to the x value is the image. I'm going to write this in a different color so it sticks out. This is the vocab word, is the image of x. So we use the word image to talk about the y value that corresponds to the x value. The image of x. Another thing it's called is this the value of the function. Oh, you little. Gotta go ahead and erase it. Using the eraser. All right. It's called the image of x, or the value of f at x. So the value, and so actually I'll make this one blue too, because the value is sort of the vocab word I'm getting at here. So we use the word image and value in that sense. We already talked about domain and range. The domain is the input. input, the range is the output. And that's pretty much, that sort of hits all the book right there. And so a map, like we talked about before, is one way of defining a function, but functions can be defined in other ways as well. We can define them as sets of ordered pairs, where one of the members of the ordered pair is the domain, is part of the domain, the other one is part of the range, and the ordered pairs tell us how the functions are linked up here. So I'm going to give you some sets of ordered pairs here that represent relations, and I want you to tell me, just like you did before with the mapping, whether they're functions or not, and also identify for me the set of the domain and the set of the range, okay? So let me go ahead here in the first example. And so because this is a set of things, I'm going to open up with a brace, and then I'm going to fill it up with ordered pairs. So like 2, 3, 5, 7, 3, 3, 9, 2, and 5, 2. So I want you to identify the domain of that function, identify the range. And within the ordered pairs, the domain always goes on the left. The value that is from the set of the range always goes on the right. That's just the way that we do that. That's the way it's defined. And then do the same thing with the next one. Identify the domain, identify the range, and tell me whether it's a function or not. Whoops. Okay. All right, so the first one is a function or not a function?
Not a function.
Not a function, because we see that 5 is linked with 7 and 2, so we have a member here of the domain that is linked with more than one element of the range, so that's not a function. What is the domain?
2, 3. Do you want the same number twice?
No, don't repeat any numbers.
2,
So,
3, 5, 9.
yep. So that's my domain, and then my range is going to be 3, 2, and 7, right?
Where's the 7?
Next to the second.
Oh, I missed it.
The next one, function, not a function.
Function.
Function. So we have, and this is okay, right? We have an element of the range here that's linked up with more than one element of the domain, but that's okay. We don't mind that. It's still a function in that case. And so it is a function, and so the domain is -3, 2, 5, and 7. And the range is, and I like to order them from lowest to highest, is just 1 and 3, right? Once again, don't repeat, order from lowest to highest when you're specifying your sets, the domain, the range. All right, so these sort of really get at the basic idea of what a function is, and that is mappings and sets of ordered pairs. But generally speaking, when we're talking about functions in this course and from this point forward in calculus as well, we're going to be specifying our functions or defining our functions in terms of equations, as you're probably familiar with. So we're going to get into that right away. I mean, we get the basic idea of a function down, we got our terminology, and now we need to expand this idea to functions defined by equations. Right? And so a really basic function defined by an equation would be like y is equal to 3x minus 2. In this case, it's an equation that relates some value of x to some value of y. So if I take a value of x and I multiply it by 3 and subtract 2, it gives me a value of y that relates to that value of x, right? Because they're equal to each other. And so this is a way of, this equality here, this equation is a way of relating the set of x to the set of y. And the question is, well, what numbers can we, what numbers are in that set of x and what numbers are in that set of y? And either it's going to be explicitly defined. I could say that x is only this, this, and this. And so you plug it in and it'll spit out all your values of y. Or it might not be specified, in which case we're going to just go ahead and assume that any value that can work for x and give me a real numbered value of y is going to be part of that domain. And so, for instance, like in some cases, I might say my domain, I might restrict the domain or specify the domain and say the domain is just 1, 5, and 8, right, let's say. And so knowing the domain, because you know how the domain and the range relate to each other, and generally speaking, we're going to use x to represent the set of the domain. I mean, really we could do it either way, but just by sort of the practice that mathematicians have used, x is normally our domain, y is our range, but really that's completely arbitrary. I could say y is a domain and x is a range. There's really no reason that I couldn't say that. It's just that it gets confusing and it's hard to tell, like, which direction we're trying to push this in if that's not the case. So generally speaking, or almost always in this class, x is always going to be the domain and y is always going to be the range with our functions. Okay, so x is my domain, y is my range. And so if I want to know what my range values are that correspond with those domain values, I can just plug them into this formula because it tells us exactly how the domain is related to the range. So I don't actually have to know the range. All I have to know is the domain, and the function will tell me what the range is going to be, which is nice because that's half the amount of information I have to know about the function. If I know the domain and I know the equation, then I automatically can get the range. And so we can go ahead and find the range by just going ahead and plugging in. We can use a t-chart for this, right? And so if my domain was 1, 5, and 8, the y values that correspond with that, well, 1 times 3 is 3, minus 2 is 1. So 1 corresponds with 1 from domain to range. 5 times 3 is 15, minus 2 is 13. Then 8 times 3 is 24, minus 2 is 22. So 1 goes to 1, 5 goes to 13, and 8 goes to 22. So we can take this function that's been defined by an equation and we can actually write a mapping for it if the domain itself is finite, meaning there's only a certain number of elements of the domain. Now, in most cases with equations, we don't actually restrict or specify explicitly what the domain is, right? I just give you an equation and you're sort of expected to figure out what it is. But before we get into that, let's talk about, so first of all, is this a function just by the way we're looking at it right here? Because not all equations are functions, of course. Yeah, because if I plug in, there's no way I can plug in 2 different values of x and then have that spit out a different value of y, right? If I take 2 different numbers and multiply them both by 3 and subtract them both by 2, I'm going to end up with 2 different numbers, right? All the time. So this has to be a function just because the nature of how these equations work. There's no way I can not have this be a function. But that doesn't mean all equations are functions, right? And the fact that we're able to solve this for y is one of the things that sort of hints at the fact that this would be a function. Now, what's an example of something that might not be a function? Well, let's what is that right there? It's a circle, right? Centered at the radius of,
4.
so this is my circle. So is this, actually, I can't do that. So is a circle, is that a function? No, why not?
Well, repeats in the backwards, right?
Yeah, and we haven't gotten, there's a rule that we're going to develop later, but for now, we can think about it as, well, let's say the value of x is 1, right? Are there two values of y that correspond to that value of x, 1?
Yeah.
Yeah, up here and down here, right?
Yeah.
So that means that it can't be a function, so not a function. Algebraically, we can also sort of see that. And it becomes very clear when we solve for y in this case. So if we go ahead and solve for y, we're going to see also that this can't be a function. How do I finish solving for y here? I'm going to subtract the x squared first. I almost have this y in terms of x. So I get y is equal to the, what type of square root? It's got to be the plus minus. So for any value of x that I plug in, I get the plus or minus of that square root. That's two different possible values. This is y, this is not a function, right? So, not a function. So not all equations define functions, but they all do define relations, right? Because they relate x to y in some way that might not be as a function, but it still relates the two. So, sort of a review here, but we are going to start using functional notation for our equations here. Right, so with functional notation, instead of saying that we're going to just start calling y f of x, right, which is, of course, that is pronounced f of x. And this is not multiplication, right? That's the biggest thing that people get confused by when they're first introduced to this terminology. That's not f times x, we're saying f of x, which means the function, which we're going to call f from now on, but we might use different letters to specify to, we might call it g of x or h of x or whatever else of x. But whatever the function's name is, if I say f of x, what I mean is what is the value of the function, the y value, which is y equals f of x, right, when x equals whatever, right? And in functions, we have a special name for the domain x that's called the independent variable. So the domain variable, whatever that happens to be, is the independent variable. Normally it's x and y, but sometimes, we can really use any variable we want for the domain, the range, right? If we're using x and y, then x is almost always the domain and y is almost always the range. But if we're using different variables, then it has to be sort of told to you in some way which one is the domain and which one is the range. But in any case, whatever the domain variable is, we call that the independent variable or the argument. And that is the input, right? Because x doesn't really depend on y. We plug in a value of x and it spits out a value of y. So y really depends on x, right? Whatever y happens to be depends on what value you plug in for x. And that's why we call y the dependent variable. Right? And so if we have a statement like f of 3, that means what is y when x is 3 in the function f. Right? That's why this notation is useful, because we can make statements like that without having to write all of this out, right? Otherwise, we would have to write out this whole sentence every single time. So it's easier just to say f of 3, and then we all know what that means at that point. All right. So, for instance, let's look at an example here. Some function f of x, which equals 2x squared minus 3x, let's say. It's defined by that equation right there. So, essentially, once again, f of x is just a fancy way of saying y, right? And it's also telling us that we're naming the function f, so that now if I go ahead down here and start saying things like f of 2, f of 0, f of 2 plus f of 1, or 7 f of 0. Well, not f of 0, that doesn't make a lot of sense. F of 1, let's say. Whoops, what is going on with that? 7f of 1, or let's say something like f of negative x, or f of x plus 2. So in each case, whatever we plug in on the inside of this, oh boy. Whatever we happen to plug in on the inside of this set of parentheses is what we're plugging in for x, and then we're going to go ahead and evaluate this expression and see what it gives us for a value of y. Sometimes we can take multiple and add them together, or multiply them by a constant, or we can plug in variable expressions for x as well, which all just means the same thing. We're going to take whatever this is and substitute it in for x in our expression here. So once you go ahead and take these 1, 2, 3, 4, 5, 6 expressions here, I'm going to spread this apart actually, and figure out what they are equal to. And bonus points if you can tell me what the graphical significance of f of 0 is. So
I'm sorry, say it again.
if you take f of 0, that's fine, no. If you take f of 0 for any function, that always is going to give you the y-intercept of the function, right? Because that's saying what is x, sorry, what is y when x equals 0, and when x equals 0, you're always on the y-axis.
If you're doing a graph like algebra 2, that's just plugging 0 to the x coordinate.
Exactly, yeah, it's just a fancy way of saying that, essentially. All right, let's go ahead and evaluate all these here. So f of 2 is 2 squared, right? 2 squared is 4 times 2 is 8, minus 3 times 2, so 8 minus 6 is 2, right?
6. I'm going to be more happy that
Oh,
this
it's
actually fit on one page
Yep.
perfectly than I got.
And if I plug in 0, this is an easy one, right? 0. So f of 2 we already decided was 2. F of 1 is just 1 squared times 2 is 2, minus 3 is negative 1, right? So we're going to do 2 plus negative 1, which is going to be 1. 7f of 1 is just 7 times what f of 1 is, which is negative 1, so negative 7. F of negative x, what happens when I plug, we're looking at the variable expression ones now, which are a little bit more tricky, or a little bit trickier. What happens when I plug in negative x for x here? What's negative x squared? Negative x is just squared, is just x squared, right?
Yeah.
Negative x times negative x is just positive x squared because the negatives cancel. So that doesn't change that part. It's still just 2x squared. Whoops, let me do this in blue. It's still just 2x squared. But what happens when I plug negative x in for x here? We end up getting plus 3x, yeah. So it actually changes the function a little bit by plugging in negative x. That's going to be important when we start talking about whether a function's even or odd and whether we have y-axis or x-axis symmetry. And the next one's going to involve a little more algebra because we have a squared here. So I'm going to actually do this next one here, f of x plus 2 on the next page. And so I'm going to hit plus. Ourselves, the function was f of x equals 2x squared minus 3x. So f of x plus 2 is going to be equal to 2, and I'm just going to put it in and then I'll simplify it afterwards, minus 3 times x plus 2. So all we're doing, once again, is we're substituting the expression x plus 2 in for x wherever we see x in the expression, right? Does that make sense? Yeah. Just a substitution, just like we were substituting a number, except in this case we have an algebraic expression. And we're going to go ahead, just like we took negative x and we simplified that by squaring it and then multiplying it by 3. How do I deal with x plus 2 squared here? What do I have to do here? I have to FOIL it, right? I can't just do x squared plus 4. So if I FOIL it out, I'm going to sort of do this in my head here. I'll get x squared plus 4x plus 4, right? And then over here we have minus 3x. Make sure the negative sign gets distributed to both terms, right? So we get minus 3x minus 6 and we should continue to simplify until it's totally simplified. So we'll end up with 2x squared. I'm going to do this last two steps in my head here. 2 times 4 is 8x, right? Minus 3x is 5x. And then 2 times 4 is 8. Minus 6 is 2. So that's what we get if we plug in x plus 2 for x. So f of x plus 2 would equal that. Okay, so we can plug in algebraic expressions with this terminology as well. Question? Any questions about that? All right.